Hi, good afternoon everyone. My name is Kazuya Sakai and I am an associate professor at Tokyo Metropolitan University. Today I'm going to talk about a user-based bike return algorithm for docked bike sharing systems. And this is the outline of this talk. First I will provide introduction to BSS and then I will provide related works. And then I will talk about problem formulation. And then I will propose user-based bike return algorithms. And then I will talk about performance evaluation. And finally, I will conclude this paper. Docked bike sharing system is now hot topics. A BSS addresses the last mile connection issues where users can randomly return bikes from stations. Docks mean that the designated space to randomly return bikes. For example, City Bike is an example of BSS. The issues of docked BSS is that users' demand to rent and return bikes differs from station to station. This causes the unbalancing problem of bikes among stations. The unbalancing problem occurs from two kinds of events. The first one is the overflow event, where there is no available dock to return bikes. For example, figure 1 shows the overflow event. There are many bikes in a station, but there is no available dock to return bikes. The second one is underflow event, where there is no bike to rent. Figure 2 shows an underflow event. In this figure, there is no bikes. So in this paper, we will address the rebalancing problem. There are many works for BSS. The BSS can be divided into two types. The first one is the dockless BSS, where there is no particular station for user to rent and return bikes. The second one is the docked BSS, where there are stations, each station has docks. In this paper, we focus on docked BSS. There are three kinds of approaches to address the rebalancing problem in docked BSS. The first one is the track-based approach, where tracks is used to move bikes from a station to station. The second approach is worker-based, where workers are recruited to move bikes. So these two approaches, the platform have to pay additional costs to recruit track workers. The third approach is incentive-based, where incentives are given to the user to avoid overflow and underflow events. In this paper, we apply incentive-based approach. Next, we will formulate the problems. In a BSS, there are n stations, and each station has a capacity. And we assume the time is discrete. And the user demand consists of 4 pieces of information. And the BSS service works as follows. User U rent a bike from station S source at time T source. If S source is underflow, she cannot rent a bike. Otherwise, she can rent a bike. And she returns the bike to station S destination at time T destination. If S destination is overflow, she cannot return a bike. Otherwise, she can return a bike. In addition, we define the state of stations. We define IFTI as the statistics of user renting and returning bikes at station SI at time T. And we also define the lambda TI as the status indicator of station SI at time T. The lambda is defined as follows. If the lambda Ti equal to 2, the station SI is overflow. And when this value is equal to 1, station SI is reaching overflow. If this is the 0, this means that the station SI is in good standing. If the value is negative 1, the station SI is reaching underflow event. And the value is negative 2, station SI is underflow. The idea of incentive-based rebalancing approach is shown in the figure. Assume that user U is renting a bike now, and her original destination is station SI. and assume that the station Si is reaching overflow or is already an overflow. In this case, we have to avoid for user U to return back to station Si. So BSS platform asks user U to return alternative station to station Sj. So in this case, user U have to walk from station Sj to station Si. Instead, the BSS platform provides incentive, additional payoff to user. So if the payoff is greater than the cost, user U can accept this recommendation. So this is the idea of incentive-based rebalancing. In the incentive-based approach, there are two kinds of costs. The first one is the incentive cost. This is the cost that the BSS system have to pay to user when asks them to return back to alternative station. The second cost is the refusal cost. This is the cost induced by event that the user cannot rent or return bikes at the source station or destination station due to underflow or overflow event. The first issue that we have to address is how to determine the incentives. We define QST and RST as a weight, and in addition we define CST be the cost as a cost that the BS system had to pay after T time slices. The incentive is determined by the objective function as follows. Now we are ready to define the rebalancing problem for duct BSS. The input includes the set of bike station S and the user demand pi of user U and walking distance Dij that the user U need to walk from station Si to station Sj, and the maximum distance R that user U is willing to walk. And then our algorithm will determine whether or not to incentivize user U to another station. If needed, recommendation optimal station OS will be outputted. In this paper, we propose user-based bike return algorithm called UBR. UBR provides incentive to users in order to avoid overflow and underflow event, and our solution is based on genetic algorithms. The scheduling scheme in UBR consists as follows. The system collects user demand large pi. If the number of bikes at station SD exceeds its capacity, an alternative destination station is recommended. The parameter of SD at time t, denoted by R, is set to be 1 and the optimal station OS for each user is computed. Otherwise, bikes are returned to the original station SD. We defined the objective function in order to define the optimality. We define the number of refusal and returning bikes for station Si at time t. R is computed by large X negative large P, where large X BTR is the number of bikes at station Si after rescheduling. And then we define the objective function as follows. So we want to minimize the cost. The left-hand side of the inner parenthesis is the incentive cost, and the right term is the refuting cost, and we sum up these costs from time equal to 1 to t. So basically we want to minimize the cost. This is the seed code of the proposed UBRs. The input includes the 4 parameters and output is the OS, and the genetic algorithm is applied to solve the objective function. Then from line 10 to 12, we compute that if the Fj is acceptable alternate station or not. If so, we compute the difference between the current and the optimal state of station Sj, which is defined by CJT. If this value is positive, this means that the status of station Sj become better after we perform the rescheduling. So if this value is positive, we assume that the user U will accept the alternative station Sj. Otherwise not. Eventually we will compute the optimal station such that the maximal the variable C. In this paper, we conducted a simulation in order to evaluate the performance of the proposed systems. We apply city bike trace, which is the real trace of the BSS. And this trace includes the historical data of a BSS in New York cities, which collected from September 1st to 30th, 2019. The first part is used as training dataset, and the second part is used to validate. And we define D as a preferential price, and we set the selection rate alpha to be 0.28 plus 0.15 log D. In addition, we set the simulation parameter as shown in the figure. The number of stations equal to 10, and the number of ducks at each station are set to be as shown in the table. The parameters for genetic algorithm is said to be as follows. The population begins to converge after 300 iterations, and the minimum value of the population stabilizes at 1.2 times 104 scope, and each parameter of the genetic algorithm are shown in the table. This is the simulation result without incentives. The x-axis shows the time slot from midnight to midnight, and the y-axis shows the number of available bikes at a particular station. For example, a positive value means that there are available bikes, there is no problem. The issue is that the negative value. For example, at 8 a.m., the value of y-axis is negative 3. This means that there is no bike, but there are 3 demands from users. In addition, at 6 p.m., the value of the number of available bikes is negative 5. So there are many demands from users, but there is no bikes. If you see this figure, most of the time during business hour, there is no bike to be rented. This is the result of the UBR algorithms. The x-axis shows the time slice from midnight to midnight, and the y-axis shows the number of available bikes at a particular station. Now, if you see this figure, there is no negative value at any time slot. At 6 p.m. there is no bikes. No. The y-axis is 0, so there is no bikes. But the other time slot, there will be a bike. So our proposed algorithms keep the station in good standing. This is the result of the success rate of UBR. X-axis shows the date from September 1st to September 29th, and the y-axis is the success rate. So if you see this figure, at least 98.6% of renting and return demand is met. In other words, our UBR successfully provide BSS services for most of the times. This is the result of operation cost. The x-axis is the time slot from midnight to midnight, and the y-axis is the operating cost in terms of dollars. The black line shows the result of UBR, and the red line shows the result of the worker-based approach. If you see this figure, most of the time, UBR incur a smaller cost compared with the worker-based approach. This is because that in the worker-based approach, the system has to pay additional cost in order to recruit a worker from the outside of the systems. On the other hand, incentive-based approach, we only provide incentive to the user inside of the BSS services. Finally, I will conclude this paper. The BSS has emerged to address the last mile connection issue, but it suffers from the unbalancing problem. So in this paper, we propose a user-based bike return algorithm for rebalancing BSS. And we conduct a simulation for performance evaluation by using real traces. And the proposed UBR significantly alleviates the unbalancing problem of a BSS. That's all. Thank you very much.